सब क्लियर है? चलें क्विकली रीकैप कर देता हूँ मैं लास्ट लेक्चर को. So in the last lecture there were three main topics. The first one was the implications of the Cauchy-Riemann conditions, and we said that if a function is analytic in a complex plane for which the modulus of the complex variable z is less than infinity, then that function is an entire function. And exponential function was an entire function. So the linear combination of the exponential functions, whether you have positive z as in the exponent or negative z, which is a complex variable, it is still an entire function. So sine hyperbolic, sine, cosine hyperbolic, all are entire functions. And then the ratio, which is sine over cosine, is not an entire function, the tangent, because cosine becomes 0 at when its argument becomes 90. So you can say that, okay, then we have something that 1 over 0 at 90 degree. So this has a singularity or pole, you can say, therefore it is not an entire function. And then we have studied is that suppose you have a function which is analytic in the neighborhood in around some point, let's say z is equal to z naught, then you can Taylor expand that function, right? And then what you have written is, you have written that f of z is summation n goes from 0 to infinite an z minus z naught to the power n. And you can see that this is a regular function, or I can say that this function has a regular part which is z minus z naught to the power n, because if you calculate f of z naught, then this becomes 0, right? So it is well defined that z is equal to z naught. And then what you have written is an, which is the coefficient of the series. For any n, you can calculate it like 1 over n factorial, then the derivative of the function with respect to the complex variable f of z at a point where you are interested to calculate the differential, which is z naught. So it means that the derivatives will definitely exist at that point, because this function is a regular function. And this, then what you have done is you have calculated the, yesterday I made a statement that is known as a radius of convergence, but perhaps that is too bold to say radius of a convergence. Let's say it's a region of convergence, because once you make a closed curve, then you can say that, okay, so it's a radius of convergence, but better to call it as a region of convergence. So how you can calculate the region of convergence, which was 1 over r, I have defined it like this one. It is the ratio of the n plus 1th coefficient to the nth coefficient, and this should be less than 1, right? Less than 1 over r, or this should be less than 1. It means that the coefficient of as you have higher and higher term, the higher term's coefficient is smaller than the previous term, right? For example, n plus 1th term coefficient is smaller than the nth term coefficient. That is why you have this less than 1, because this is, if you expand it in the neighborhood, then this becomes a small number. Okay, so using this, you have calculated the region of convergence for the exponential function that came out to be infinite, right? Because then, if you remember, I don't need to do it again. What was the next point? We know that f of z is an analytic function. If I can write f of z and divide it with something which is also, you can say, an analytic function, because z minus z naught in itself is an analytic function, because partial f by partial z star for this denominator is 0. And you define a new function which is f1 of z. The problem is this function has a singularity. This function has a pole at z is equal to z naught. This has no problem, but this has a pole. So if you integrate this function, then there is a Cauchy's integral theorem over a closed curve, and what you got is yes, f of z naught was 1 over 2 pi iota, and then f of z over z minus z naught dz. Very good, thank you. So I said that you can mention the direction of a pole, which was the direction of increasing angle theta. So the good thing about the analytic function is if it is analytic, all of its derivatives are analytic in that range also. Because e to the power z is analytic, you can take as many derivatives as you like, they are also analytic. So it means then you can write the differentiation formula for that also. If you just consider z minus z naught as a parameter, sorry, z naught as a parameter, then you can just take a derivative of this one, df of z naught with respect to z naught. Because this z naught can be anywhere in the region, and you can just make an expansion around that point. Then you can just calculate it as partial by partial z naught of 1 over z minus z naught, because only it has z naught, it has no z naught, so you can write it as dz. So it means from the simple z minus z naught, which is kind of a linear term in the denominator, you have higher part term also. So then you have squared, cube, up to so on and so forth. So, and there is of course a factor of 1 over 2 pi iota. So from this you have calculated the nth derivative. So you have written it in the form of n factorial. And if you remember, you have written dn f of z naught over dz naught, then this is equal to n factorial over 2 pi iota, and then closed integral f of z over z minus z naught to the power n plus 1. Okay, good. Yes, if you're right. And then here you have n. Exactly. Thank you. So this is all fine, right? And do you know what is this one? By the way, you remember what is an? Recall this. You know this is an. So if I calculate everything at z naught, I can write an is equal to 1 over n factorial then, right? So it means that if I take this on this side, 1 over n factorial, then I can just write an in terms of this one. So it means 1 over n factorial, and if I multiply it on both sides with this one, this will cancel. And then I have 1 over 2 pi iota on a closed contour f of z over z minus z naught to the power n plus 1 dz. This is equal to an. So you can see that it is not only that I have written the coefficient of a Taylor expansion in terms of a differential, but if that function is integrated over a closed curve, then you can also express it in terms of this integral. This is remarkable. You see, you just need to calculate this one, and then you can calculate the corresponding coefficient. If I ask you, you have to calculate a2, then it is f of z, z minus z naught cube. All you have to calculate is this one. Today we'll practice some of examples related to this. So this we have done except this step. So if you have any question, then I guess I have done something else also. I made some small things about that, and you remember that in f of z I have done one more thing yesterday. So let me write it, and because that's the starting point for today's lecture. So I said that in any, you can make f1, which is f of z over z minus z naught, even if you write f of z as summation over n, which runs from 0 to infinity. So you can see that n is positive number, or 0 or positive number greater than equal to 0. And if you remember, I told you that z to the power n for n greater than equal to 0 is an entire function. So it is analytic. So this is then an z minus z naught to the power n. This is regular part, there is no problem. But why not I can just add a minus 1 over z minus z naught. You can, I have written just minus 1 just to ensure that if I generalized it to n, then I put minus n over here. I can write the series exactly like n goes from minus infinite to infinite, and I'll do that. Now you can see, at z is equal to z naught, this is regular part, and at z is equal to z naught, this is singular. This is singular part. It's fine. Add kiya. Just to make this function looks like f1 now. It has a regular part and then it is a singular part. I can add another term, another term, another term. I'll come to this point. If you have a linear term in the denominator, then this is kind of a simplest pole that you have. That is why we call these kind of singularities a pole as simple pole. So whenever you see a pole like 1 over z, then this becomes a simple pole. So imagine if you remove this pole, what you will get then? This coefficient, bachi kuchi cheez, that is known as a residue. So this is the residue coefficient for that. So today we'll discuss that how we can remove these kind of poles and then find out the corresponding residues. And then we go to the residue theorems. So it is kind of a step-by-step thing, you know. And let me give you an example that how we can calculate this thing. Let's take, for example, this. Let's take this kind of function. F of z is equal to sine of z over. Let me. I guess I have. That's fine. F of z is sine of z over z squared. And you know that for small z, so before that, if you remember this sine z over z, this is a function that if you have z is equal to 0, this is kind of 0 over 0, which is you cannot determine, it's indefinite, undeterminate function, yeah, whatever you call it. But if you expand it around small z, then you have a constant value which is 1. And you can see that it has no pole at small z. If z is small, the first term is 1. So this function as z approaches to 0 is 1, and if z is not equal to 0, this function is 0. Sorry, this function is sine z over z. So if you have sine of z over z squared, and if you expand this function around small z, then what you can write is, you can write z minus z cube over 3 factorial, let me write a few terms, z5 over 5 factorial plus up to so on, divided by z squared. Now divide it with z squared. You have 1 over z minus 1 over 3 factorial into z plus 1 over 5 factorial, and then you have z squared, and then you have minus so on. You can see that this is something which is kind of a z to the power anything, any power, I'm saying m can be along with some coefficient of 1 over 2m plus 1 factorial, right? 2m plus 1 is, if you have m is equal to 1, then you have 3 factorial, m is equal to 2, you have 5 factorial, plus minus, not summation, but this is with alternate sign, so you can write it as minus sign over here maybe. But just look at this function term, 1 over z. You have exactly this kind of function, a n z, a regular part, instead of calling it a z to the power m, let me call it as a regular part, because this is a far better definition. So this is you have a regular part, and then you have something which has a simple pole. And what is the coefficient of this simple pole for this term? So this implies is a to the power minus 1 is equal to 1. So this is the easiest way. You expand the function in the neighborhood of that point and look at the coefficient of 1 over z term. If it has no 1 over z term, like for example you have e to the power 1 over z squared, and if you expand it, you have 1 over z squared plus up to so on. It has no 1 over z term, therefore it has no residue. So this is known as the residue, a to the power minus 1. Let's make it more, let's elaborate this point a little bit further and make it general. And this definition is way more general, which I'm going to do now. Suppose you have two functions, f1 of z, that is analytic, f2 of z, that is also analytic. And then take the ratio. Exactly like tangent. Sine is analytic, cosine is analytic, take a ratio. Because if we take a ratio, it will not necessarily be an analytic function. So let's take f1 of z, a function, and let's take f2 of z, a function, analytic function, and let's define a new function which is f of z. Let's make a few assumptions. Let's consider, or you can assume that f1 at z naught is not equal to 0. And you can always take f2 at z naught is equal to 0, because if it is also 0, then you have 0 over 0, which is not a good sign. So it's even you can just take any value for that. But let's be very simple, that the f1 at z naught is not equal to 0 and f2 at z naught is equal to 0. And I just wanted to expand this function in the neighborhood of z is equal to z naught. What will be the answer? Any suggestions? Any suggestions? F of z. I told you how we can expand the function in the neighborhood of something. Very good. Yeah, exactly. So you can write f1 at z naught plus z minus z naught f prime at z naught plus up to so on and so forth. And then you can also write, sorry. F1, sorry, exactly. Thank you very much. Thank you. And you can do same with this one, f2 at z naught plus, then you can do z minus z naught f2 prime at z naught plus up to so on. Now imagine you are in a very close neighborhood of z is equal to z naught, in neighborhood of z naught. It means the higher parts of z minus z naught becomes very, very small. So let's ignore those parts. And you remember this, in my assumption, this is 0. Then what you have? You have f1 of z naught plus, let me write it, f1 of z naught over z minus z naught and f2 prime of z naught plus, this is gone, so then you have f1 prime at z naught and over f2 prime at z naught. And you remember that, I just want to show you this pole, z minus z naught. What is the residue in this case? If you just compare it with this thing, this one. So you can say that, okay, the better way to write a to the power minus 1 is f1 at z naught over f2 prime at z naught. So suppose you are given a function and you will be asked to calculate the residue of that function in the neighborhood of a point which is given to you. It is just the ratio of these two. Provided f2 prime exists.
Exists, but if it's 0,
it's not 0. Yes, exactly. F2 prime should exist. Exactly. All derivatives of f should exist. They are not equal to 0. You are right. I can give you a simple example for that also.
So अगर f2 of 0 not हम z not हम 0 ले रहे हैं तो उसका डेरिवेटिव भी 0.
नहीं वो यही तो सारी रामलीला थी ना. f of z naught जब टेलर सीरीज खोली, डेरिवेटिव्स लिए, फाइनाइट था, एक डेरिवेटिव एग्जिस्ट किया, सेकेंड, सो ऑन सो फॉर, सारी डेरिवेटिव एग्जिस्ट किए थे.
तो जब हमने ये यहाँ से a minus 1 equals to 1 किया ना, तो हमने just compare किया था कि a of minus 1 उसके साथ क्या था.
अभी भी करूँगा.
यहाँ पर हमारे पास जो है ना वो एक सिंगुलर पार्ट है और एक रेगुलर पार्ट है, और सिंगुलर पार्ट में एक क्वांटिटी है. फॉर एग्जांपल अगर हमारे पास सिंगुलर पार्ट में दो,
I'll come to this point. I'll come to this point. Then sometimes you have essential singularities. Means like you have 1 over z minus z naught to the power m. Then you cannot say that removing z is equal to z naught in a linear term will remove the singularity. I'll come to this point. Definitely. In few minutes I'll come to the point that how you can find the order of a pole. Right? And then you have to make a mechanism to remove those poles also. I'll come to this point, definitely. Okay, let me calculate it for a very, very simple example. So, and you remember my assumption was f1 and f2 were analytic functions. So first thing you have to check these things. So instead of doing things with the brute force, first check if the basic assumptions are fulfilled or not. Because if they are not fulfilled, then answer will not make any sense, even if you get some sensible numbers also. So let me give you an example which I have done. For example, you have f of z is equal to simplest one, very simple one. F of z is equal to z squared plus 1 over z minus 2. Right? And you have to calculate around z is equal to 2. Because at z is equal to 2, it is infinite. Is it analytic function?
yes.
Take a derivative with respect to z star, it is 0, therefore analytic. Is it analytic function? Yes, okay. Now you can calculate, so you can say that, okay, f1 of z is z squared plus 1 and f2 of z is z minus 2. And I'm just wanting to calculate around z is equal to 2. So then you can calculate f1 at 2, which is 5, and you can see that f2 at 2 is 0. It's kind of exactly what I have done over here. So f1 is non-zero, f2 is 0. So I have done a very specific choice. Now what you have to do is, you have to write f1 at z naught, and you have to take a derivative of f2. So take a derivative of f2 prime at z is equal to 2, no, at 2, which is equal to 1, exactly, it's a number. And you can just substitute it over here and you can get the residue. It was very simple. If you have squared z squared minus z squared plus, for example, 1, then you have two poles, z plus iota and z minus iota. If I ask you to calculate in the neighborhood of z plus iota, then you can see how to do it. So then you can say that a minus 1 is 5, right? 5 over 1, which is 5. How about other simple one? You have to tell me. I'm not going to do it. How about this one? F of z is equal to e to the power minus iota omega z over omega squared minus omega naught squared. Around omega, amount the positive value of around omega is equal to omega naught. What will be the answer? E to the power minus iota omega. Exactly. What you have to do is you have to write it as a minus b into a plus b. So you have to substitute omega is equal to omega naught, and then you can differentiate that. Differentiate it, you have 2 omega. Put omega is equal to omega naught, you have this one. So this is how you can determine the residues. Oh, कुछ गलत लिख दिया मैंने. Z square minus star. Yeah, you can write anything you like, no problem. Okay. No problem. You can write anything you like. Okay. Z square minus omega naught squared. Right? Then you have to write it this one. And then you can do it. Okay. You are saying this one. Z squared minus omega. Right. Thank you. Exactly. So, by the way, this is one way of doing it. Other way of doing for the simple pole is Why don't you multiply your function with something that has, with the pole term, z minus z naught? Because that was way more easier than doing all these things for the simple pole. And that is, just multiply your function with z minus z naught and then take the limit z goes to z naught, and this will be your a minus 1, which is the residue. By the way, you can prove it in a very, very quick way. Because you know the first term has a Taylor sum that has z minus z naught to the power n. So if you multiply that with z minus z naught, you have n plus 1, but at z is equal to z naught, this is gone. And a minus 1 over z minus z naught becomes a minus 1, therefore you have the residue. So for simple pole, life is very, very easy. But it is not necessary that we always have a simple pole, as you said. So let's do some exercise and add other terms, you know, because you remember I have written a series like this one. You can say that why don't you write f of z as summation n goes to 0 to infinite an z minus z naught to the power n, which is the regular part, Taylor part, plus summation m, and then you have, let me write it as cm over z minus z naught to the power m. By the way, it's good to have m is equal to 0. You can just start with m is equal to 1, right? So you can start m is equal to 1 to say anywhere you can go. Okay, so to infinity 1. नहीं नीचे आ रहा है ना. It will go upstairs, then it becomes minus. I'm doing it. I'll combine it later, you know. But there's a better way to write it like then. Okay, there is a better way to write it. Summation n goes from minus infinite to infinite, and then you have an over z minus an into z minus z naught to the power n. When n is negative, you have this part. When n is positive, 0 or positive, you have this part. So this way of writing a series is known as a Laurent series. So Laurent series is kind of an extension of a Taylor series in which you have singular terms, and which are these kind of terms. Got it? Now I have to make certain claims, and I will justify all those claims. By the way, if I ask you that, can you calculate the CAN and CM? Can you tell me how to calculate AN and CM from the function? You have written, quite recently you have written 1 over 2 pi iota integral over a closed contour f of z over z minus z naught, exactly, on a closed contour n plus 1, and then dz. What will be Cm then from this series? Go home, repeat all these exercises. What will be the answer? Any bold guess? Minus m. Very good, very well done. Absolutely. You can write it as, very good, 2 pi iota, and then you can write f of z over z minus z naught to the power minus m plus 1 dz. Absolutely. What you have to do is, you remember you have written it in terms of a differential. You remember? And from there you have calculated dz. Then again you can do the same exercise and calculate the coefficient of this Laurent term, of this singular term. Okay, good. So with this one, let me make certain claims, and then I will justify all those claims one by one. Okay, so the first one is if CMs are 0, it means the function will become analytic. function will become regular function. If certain CMs are 0 or non-zero, and above those numbers, let's say I have any, let's see, C1 and C2 are non-zero, then C3 up to so on are all 0. It means I have poles of not only simple pole, but poles of the order 2. So till the coefficient which are non-zero, that will define the order of the pole. And the last thing is, if I multiply Z minus Z naught with the function, and there is no term that is Z minus Z naught on the right hand side, it means the pole was simple pole. This you have already done. You have multiplied with Z minus Z naught, you have A minus 1.
So what if we multiply the function by Z minus Z naught power?
Okay, good. Right, exactly. I'll multiply this with order of pole, then take a differential and then put it and calculate the corresponding stuff. But is it equal to the residue part, first part, simple pole part, or the other parts will also contribute? This will prove in today's lecture, definitely.
Sir, isn't the derivative form of the coefficients easier to calculate than the integral form?
Exactly, that's, but it's, there is one thing that there is one very important point over here. You have a function which is singular. If that is the case, then you have to use this one. You have to calculate in the neighborhood and then apply the Cauchy-Riemann conditions, and then you have to calculate the residue. And then you will have a residue theorem. I'm coming to the residue theorem now, because I have explained you what we mean by the residue. Now, next part is, what is the answer of this integral? We'll come to this point now in just 10 minutes. But before that, let me finish this, what I have started, this business that someone asked me about the order of a pole, how we can calculate the order of a pole. And for that, let's assume a very, very simple function, which is f of z, which is one over z into z minus 3 cube, slightly more complicated function. You can see that it has a singularity that z is equal to 0 and z is equal to 3. And you have to calculate the order of a pole. At z is equal to 0, what is the order of pole? And at z is equal to 3, what is the order of a pole? By the way, what is the order? Exactly. Exactly. And if I ask you what is the residue for z is equal to 3, then you have to do some work on that. Let's do it. So instead of this one, let me give you a technique how to calculate it. First make this as like, you can write it as 1 over, you can take minus 3 outside, so this becomes minus 27z, so that you have something which looks nice, 1 minus z cube. Oh, sorry, 1 minus z over 3 cube. Sorry, let me erase this one. Minus 1 over 27 into 1 over z into 1 minus z over 3 cube. Now you can see that if something is smaller than z, then you can expand the series, no problem at all. Can you expand that and find the answer? What will be the answer then? You have minus 1 over 27 z. These are small exercises, but you know they will at least give you an idea how to implement these things. So you have 1 plus z, yes, then minus 12 over plus 12, okay, minus 3 minus 4 minus minus 3 minus 4, then you have minus plus 12 over 9 z squared plus next term 3 4 5, I don't remember, I don't want to remember that even, right? Okay, the good thing is for z is equal to 0, you have minus 1 over 27z plus a constant term which is minus 1 over 27 and plus or minus, you have 12 over 9 into 27 z plus or minus, I don't know, so on and so forth. So you can see that for z is equal to 0, around z is equal to 0, what is a simple pole? Because all these terms are gone, where I have a regular term, and then for z is equal to 0, these terms will go. What is the residue? What is a to the a minus 1? Minus 1 over. It's correct? It's fine. Okay, how about z is equal to 3? What is the order of pole? 1. Simple pole. Z to the power is 1. So the order of pole is 1, and if the order of pole is 1, then it is a simple pole. Now, how about z is equal to 3? What you will do? You remember the word neighborhood? And I told you that we have to expand in the neighborhood of that point. So it means that you can write z minus 3 is equal to alpha. Now do it. So implies z is equal to SL. I can write it as z naught also, no problem, whatever you like. So now open the series and tell me the answer. Then f of z becomes f of alpha, which is equal to 1 over 3 plus alpha into alpha cube. Expand the series and let me know the answer, please. Make your life slightly more easier. 1 over 3 alpha cube into 1 plus alpha to the power minus 1. This is the simplest series that you have, by the way. Alpha divided by 3. Yes, 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 please. Exactly. Thank you. Answer. So you have 1 over 3 alpha cube 1 minus alpha over 3 plus alpha square over 9 minus alpha cube over 27 plus up to so on. I have to go to the order so that I can cancel alpha from denominator. And now you can multiply this one. What is 1 over 3 alpha cube minus 1 over 9 alpha squared. 9 alpha squared plus 1 over 27 alpha minus 1. How about next term? Then it's proportional to alpha. What is the highest power of alpha? 3. So it means z is equal to 3. The highest power of the pole is 3. Order of pole is 3. What is the residue? No. Residue is always the term of which the coefficient of a simple pole. That is why I have done all this exercise, that don't mix your residue with this term. The residue is always the coefficient of a simple pole. I will prove it in a more general way.
So residue तो है वो a minus 1 वाला ही है.
Z minus Z naught, simple pole, first power.
And sir जो बाकी terms हैं.
वो ऑर्डर ऑफ पोल तो बता रही हैं आपको, लेकिन रेजिड्यू क्या है? अगर मैं एक इंटेग्रल करूंगा, अभी देखिएगा, and if that integral becomes proportional to these residue terms, then what will happen? I have to just collect the residues then, and sum of all the residues, the singular points. So it is the whole idea of this whole exercise is to tell you the order of a pole and the residue.
सर यहाँ पे इस एग्जांपल में हमारे पास दो पोल है ना, एक z equals to 0 है और एक z equals to 3 है. जो प्रीवियस एग्जांपल हमने की थी
एक ही पोल था.
उसमें सिर्फ एक ही पोल था. तो एक ही पोल के लिए वो रेजिड्यू का जो ऑर्डर था वो भी उसी से पता चलता है, और जो रेजिड्यू होता है उसका भी और पोल का ऑर्डर भी. यहाँ पे फिर वो अलग अलग
नहीं, अभी तक तो मैंने इंटेग्रल किया ही नहीं ना सॉल्व. आपको याद है an क्या है? an has a power n plus 1 downstairs. उसमें तो कोई there is no condition that n is always equal to 0. and can be 1, 2, 3. So you have 1 over z minus z naught, z minus z naught squared, z minus z naught cube, up to so on and so forth. Whatever power you have, you can close this, you can calculate the corresponding coefficient. It is not necessary that you have 1 over z minus z naught always downstairs. But now let's find a theorem, let's do a residue theorem and see what is the answer if we calculate the integral of some function which has some singularities in a region and on a closed path, and see how it is related to the coefficients of the simple pole. That is the famous residue theorem, right?
सर एक सवाल है।
Please, please, please.
सर अभी जैसे हमारे पास दो सिमिलैरिटीज थी ना, तो ये दोनों रिमूवेबल हैं?
दोनों रिमूवेबल है. So the idea of this whole exercise is to tell you how to find the coefficients. So you can find the coefficient in general from this Cauchy integral formula, and if you can expand the series in a quick way, then you can find the corresponding coefficient by looking at the series. If I ask you to calculate the residue, if you can expand the series, expand it and see the coefficient of 1 over z term. Now let me do the residue theorem. And because this is kind of you can say that's the kind of a most general thing in which we can do an integral. So let's assume that f is a function that has singularities, not one, but it has many singular points inside a closed curve. So let me draw it and imagine this is the real axis in complex plane, and this is imaginary axis in complex plane, and you can draw smooth closed curve, and it has many singular points. Z1, let's say you have Z2, you have Z3, doesn't matter how many points you wanted to have, you can have. And what you have to calculate is you have to calculate the integral along this closed path, closed curve. Any suggestion? You know the answer. You know the answer. I mean, you know how to calculate it. And the residue theorem is, you know what, is this one. Is integral along any closed path, f of z, dz is 2 pi iota times sum of all the residues from m is equal to 0 to infinite C1m. I mean, first term only, like a minus 1 if I take m to be negative, a minus 1. Now I have to prove this residue theorem, this one. So, any suggestions? Once again, the same idea. Let me make it slightly bigger. You can make small circles around Z1, Z2, let's take only 3, because it doesn't matter if we can calculate for Z is equal to 3, we can calculate for even Z if we have n poles then. What we have to do is, you have to open this and open this, join them smoothly. There is no knot. You can open this one and this one, join it. You can open this one and this one and join it. Suppose this is C1, this is C2, this is C3, all are these paths now, right? And then you have this whole path, and then you have this path was your C path, the previous one, and this new path, which after cutting these becomes, let's say, you can call it as C1. Do you think C1 has any singular point in it? So it means that whatever I can do, one thing is for sure, that integral of f of z dz on the path C1 is 0, because it has no singular point in it, which is the Cauchy's integral theorem. So start moving in a counterclockwise direction, like this one, right, comes this way, out, perfectly fine. This path is fine. You have to go zigzag, but there is no problem with it. It means that if this is equal to 0, then this is sum of C, C1, C2, C3. So now write this sum. You know what we do? Something very strange. This opening need not to be very wide. Then we start closing it. It is just known as a deformation of a contour. We deformed our contour. And then we can just combine these points again. And if I remove them, then the figure becomes very smooth. Then you have complete circle over here, complete circle, like this one, right? I can make it with some other color if possible, so that we need not to waste time to draw it again. So you have kind of a smooth curve, smooth. So you have made small circles, and if you calculate the integral in these small circles, sum them all, then you can get the integral in this C. In the neighborhood, in a unit circle around, you remember, Z is equal to Z naught. This is what we have done yesterday. So now calculate, tell me the answer. What will be the answer then?
And the paths, because they're oppositely directed.
Exactly, they cancel, exactly. Absolutely, yes. You can see that if you join the two, one is going out, other is going in, they will cancel. Absolutely. And you see that. Now if you write integral along C, f of z dz plus along C1 closed path, and you have f of z dz plus along the closed path f of z. I will define the direction of the path in a moment, plus f of z dz, and this is C2 and this is C3. I have just calculated for these paths only. This is equal to 0. And you see that this is anti-clockwise. Right? This is clockwise. This is clockwise. This is clockwise. So all small circles are clockwise. The bigger circle is anti-clockwise. So let me put the direction of contour over here also. I know maybe this is an ugly way of writing, but in LaTeX you can always write it like this one. No, this has a pole at z is equal to z1. This has a pole at z is equal to z2. This has a pole at z is equal to z3. So the problem is that these are kind of an isolated points. There is no mixture of any two. If you close z1 with a small circle, it has nothing to do with z2. z2 has nothing to do with z3. z3 has nothing to do with the other one. Now calculate this thing, and this has the answer of your question. Now calculate this. Suppose you have f, you remember what is f of z? What is f of z in general? Which is singular, which has singularity. No, in general. Minus m. Right? Now you have to calculate it. Around z is equal to z1. Any suggestion? So instead of that, let me write this. For j is equal to 1, I'll slightly tweak this index. I write it as a j and then 1. And so that I know that j is general, 1 correspond to z1. And then I write j2, so that 2 correspond to z2. And then I write is j, comma 3 without comma, so that it corresponds to z3 up to so on and so forth. So better to write it like this one. Let me write it like, for z is equal to 1, for z1. I will calculate this for only one of them, and rest you have to, at least one of the other, exactly you have to replace 1 with 2 only, but practice at least one of the other term. So you can write it as summation. So f of z is summation j is equal to 0 to infinite a, j and 1, because it is for z1, and then you have z minus z naught to the power j plus summation k is equal to 1 to infinite c k1, and then you have z minus, sorry, this is z1, z minus z1 to the power k minus k. And if you open it, then you have a10, right? And then you have a11, z minus z1 plus up to so on. And then you have, just to give you a feeling that how I have written them, C11 over z minus z1 plus C12 z minus z1 squared. Now you see, it's the answer of your question. It's not necessary that I have only z minus z1. I have all the parts of z is equal to 0. These are kind of a essential singularity. You cannot remove, it doesn't matter you remove z is equal to z1 from this term, you have singularity in this term, other term, so on and so forth. This was your question. Okay. Let's erase it. So I hope you have it in your, because this business is done already. So now what you have to do is you have to calculate only along one contour, because it doesn't include C1, Z1, it is 0. It has no Z1 involved in it, it is 0. Therefore, if you calculate this one only, the answer of this is equal to this one. So then you can write along a closed path C1 f of z dz. Let me write it like this one. By the way, it doesn't matter. If I bring it on the other sides, I have to change the directions of this, increasing theta then. Clockwise becomes anti-clockwise, so it doesn't matter. So that's why I said that if you calculate it like this one, bring it on the other side, change the direction of contour, answer will remain the same. So, okay. So it's better to calculate it like this one to be consistent. Any suggestion? You know how to calculate it. You have an idea, you have already done that. Okay. 2 pi iota. But I have whole lot of higher powers also. So how to do it? That's the problem. So you have j is equal to 0 to infinite. You have to write all these terms. A j1 z minus z1 to the power j plus summation k is equal to 1 to infinity c, oh sorry, this is k 1 z minus z1 to the power minus k. The first important thing is you can bring the summation outside and integrate it and then take a summation, there is no problem. So you can write it as summation j is equal to 0 to infinite and then a j1 z minus z1 to the power j dz. What is the answer of this, by the way? Plus, okay, let me do first thing, one other thing. Plus, let me do all others by opening the summation. So you have this one. So you have C11 over z minus z1 dz plus, this is on C1. Never forget to mention the contour C1, and then you have C12 over z minus z1 squared dz plus up to so on. Now tell me the answer. First term 0 हो जाएगी, क्यों? Analytic integral 0 होगा. Good, very good. Because if you put z is equal to z1, this is analytic function, the answer is 0. Okay, this is 0. The most important term is, let's say, this third term. Because this is no problem at all. We know this is a residue. What is the answer of this term? Any suggestion how we can calculate that? No. What I told you, take a small circle, unit circle, to solve all these kind of integrals and see if in the unit circle they are non-zero or zero. Because unit circle is, the integration runs on theta from 0 to 2 pi. So exactly what you have done yesterday. Same steps. Without going into any new technology, you can just do it for one part of k, right? So I can prove it for a general k, and you will see. I have written say k1, so this is 2, 1, not 1, 2. Let me do this integral. And then you can write all these terms as a summation again. You remember how you can write it? You can write them as summation upon k is equal to 2 to infinity and c k1 over z minus z1 to the power k. So it means if you can calculate k is equal to 2, then you can go for the next term, take k is equal to 3. But let's prove it for a general integer value of k. So you can take a small unit circle and then define z in the neighborhood of z1. And you remember exactly same technology. Z is equal to z1 plus, let's say, a e to the power iota theta, where theta runs from 0 to 2 pi, including 0 and 2 pi, right? So then it means dz becomes very good. Dz becomes a, it's a fixed radius, small radius, and e to the power iota theta, and then I have iota d theta. Then what will be the answer of this integral? Integral over the closed contour C1, and then you have C K1 over, the integral is this one, and K is of course greater than 2, So, sorry, K is 2 and above, dz, yeah, dz. And if you calculate its answer, I don't want to go into that detail, then you can have this is equal to iota C K1 a to the power minus k plus 1. It's not difficult to calculate, by the way. You have a to the power minus k and you have a upstairs, so this becomes a to the power minus k plus 1. And then you have iota over k minus 1. And remember, you have started k from 2. That is why you have k minus 1. And then e to the power minus iota k minus 1 theta. Theta runs from 0 to 2 pi. Cos is 0 at 0, and if you take difference between 2 pi and 0, sine is 0. Therefore, this integral for any integer other than 1, because my k isn't 1, my k is 2. So for any value of k greater than 1, the answer of this integral is, by the way, you see, life is very simple now. All these terms are gone. And what you have is simple pole. What is the coefficient of that simple pole? Residue. So it means that if you calculate this integral in C1, then the answer is just the corresponding residue C11. It's fine? कौन सा? इसको 0 किया. Okay. Okay, so I have written is cosine k minus 1 theta from 0 to 2 pi. And you remember I said that k runs from 2 to onward. Because if k is 1, then e to the power 0. E to the power 0 is not equal to, the answer is 2 pi then. That's why my series started from k is equal to 2. I'm solving for these terms. I said that I'm doing it for third term. So the answer is, what is the answer for this one? So this is cosine k minus 1 2 pi minus cosine, which is equal to 0. Cosine 2 pi and cosine 0 are the same. Similarly, sine 2 pi and sine 0 both are same, equal to 0. So it means that the answer of this integral is 0. नहीं, no, this is for z is equal to 1. Similar series you have for z is equal to 2. Again, you have similar series for z is equal to 3. So you can write these kind of series for all singular points. Doesn't matter how many singular points you have. The good thing is the answer of this integral is equal to the residues. Exactly, exactly. For z is equal to, when you remove the singularity for z is, pole from z is equal to z1, the corresponding residue will be the answer for that C1. Similarly, if you do the similar thing for z2, then you have C2, exactly, C12 or CK2, whatever, C12 you have, let's say. And if you have 1, 3, 1, 4, 1, 5 up to so on and so forth. So you are done with the residue theorem if you see. So this is how you can prove this theorem. And you see this part of this Laurent series then. Even though this was divergent, the function was looking very ugly, but still you have the answer to be like this one. So my answer for C1 is, along this closed path, f of z dz on this C1 is this integral. C1 and this we know what is the answer of this, 2 pi iota C11, right? Because this integral we know, if we divide it by 2 pi iota, the C11 will be the residue. How about this one? So slightly confusing notation, let's write it as small c1. I never realized that I'm writing contours as also c. Better to write it as b, you know. So what will be the answer of this one? Doesn't matter. You want to write it 2, 1, and then this is 2 pi iota C21, up to so on and so forth. So it means that if you add all of them, then the answer of this integral on a closed curve C, f of z dz, in which f of z has many singular points, is nothing but this is 2 pi iota times the sum of residues. This is known as a residue theorem. Trust me, it is very important theorem. Sometimes this calculus of complex variable is frankly called as calculus of residues, because you have to do is to calculate residues. So it doesn't matter any function you have, any series you have. If you have these isolated poles, then you can always make small circle around individual pole and then calculate the integral in that pole, which is equal to 2 pi iota times the residue, the coefficient of that term, gather all these coefficients, add them, multiply with them with 2 pi iota, and then you have a answer for the very bigger curve, closed contour, regular closed contour. So if you have any question, please don't hesitate to ask. डिफॉर्म किया कंटूर को स्मूथ ही रहने।
आपका सवाल ये है कि अगर पोल्स के बीच में फासला कम हो जाए, Z1, Z2, Z3 ये सारे पोल्स हैं, what if there is an infinite
number of poles
आप ये
कर नहीं सकते। जी जी, इसलिए मैंने सर एक लफ्ज़ यूज़ किया You can isolate them.
Isolated
Yes, exactly. I have used this word isolated.
क्योंकि उनके बीच में
जी
फंक्शन
जी
रिलेटेड है
जी
लेकिन जब वो लगातार पोल्स एक साथ
सारे पोल्स
पोल ही पोल
Please.
ये true one की बजाय 1 2 ही होना चाहिए क्योंकि
Does-
दूसरा index of
Okay, okay. Doesn't matter. That's why I've written it one m over here. Okay, okay. It means I was right. Eh? Okay, then 1m. No, fine. Thank you, Hamza. Thank you. The idea is you just have to collect the residues. That is why I used to write summation m is equal to 1 to infinity a minus m. You have to calculate minus 1, first residue from the first, residue from second, residue from third, residue from fourth, and my residue was a minus 1
सर जो हमारे पास इंटीग्रेशन होती है तो हमें ये बताती है कि लाइक एरिया
under the curve.
तो अगर हमारे पास बहुत सारे पोल्स आ गए तो फिर हम क्या उसके बारे में कहेंगे
यही बताएंगे एरिया अंडर द कर्व इसके बराबर है.
नहीं नहीं अगर इनफाइनाइट जैसे सर ने कहा कि वो सारे ज्वाइन हुए हुए हैं मतलब इतने नजदीक है वो सारे पोल
तो ये चलेगी नहीं कैलकुलेशन
एरिया अंडर द
कर्व नहीं है. हाँ हाँ
देखो जब हम इंटीग्रेट dz पे करते हैं तो वी आर एक्चुअली इंटीग्रेटिंग ओवर टू नंबर्स
x and y. yes. Yeah.
तो हाँ जो x वाला एरिया अंडर द कर्व एक तरह से इंटीग्रल ओवर y दूसरा इंटीग्रल
उसी का जवाब थोड़ी देर पहले प्रवेश ने दिया था कि इफ यू हैव इनफाइनाइटली मैनी पोल्स जो जुड़े हैं तो ये सारी चीज नहीं चलेगी.
सर मतलब उसको फिजिकली सोचने की कोशिश करेंगे कि वो इनसाइड दैट सर्कल या जो लूप होती है वहाँ पे क्या है
देखो ना यूं समझो कि पॉइंट ए से पॉइंट बी जाना है कॉम्प्लेक्स प्लेन में तो किसी पाथ पे जाएंगे एवरी डिफरेंट पाथ इन प्रिंसिपल विल गिव यू अ डिफरेंट आंसर
एक्चुअली सर वो आपके पिछले सवाल पे वो कहते हैं कि बहुत सारे पोल्स हों
हाँ
तो फिर तो जी आइसोलेटेड ना हो देन दिस इज नॉट.
तो फिर आप देखें अगर वो सारे जुड़े हुए हैं पोल 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 तो फिर आप थोड़ा सा ऊपर जा सकते हैं
यस
थोड़ा सा
नीचे आ सकते.
यू कांट इंटीग्रेट थ्रू अ पोल
सर ये आई थिंक एरिया की बात कर रहे हैं क्योंकि अगर रियल फंक्शन हो तो वो तो हमें एरिया अंडर द कर्व दे रहा है ना इंटीग्रल इसमें क्या हो
तो ये लाइन इंटीग्रल
लाइन इंटीग्रल ना तभी तो आपने सरफेस बनाई थी. यू हैव रिटन एज स्टोक्स थ्योरम एंड यू कैलकुलेटेड दिस लाइन इंटीग्रल u x dx v dy
वो तो क्लोज कर्व
और क्लोज कर्व जी
क्लोज कर्व
जी
लेकिन इन जनरल इट विल बी अ लाइन इंटीग्रल
लाइन.
तो इट मींस कि हम इनसाइड दैट लाइन इंटीग्रल हम उसकी कोई बात नहीं कर रहे
नहीं हम कर रहे हैं ना. अगर आपको याद हो तो कल हमने बनाई थी एक इसको हमने कंटूर कहा था. हमने इंटीग्रल को डिफाइन कैसे किया था f of z from let's this point alpha to beta and dz. This is my integral. When I closed it, then I have joined the 2 points and I'm doing all this calculation for the closed curves.
एरिया तो क्लोज कर रही है ना
एरिया किस प्लेन में?
जो जब आप इन दोनों पॉइंट्स को
कॉम्प्लेक्स प्लेन में.
कॉम्प्लेक्स प्लेन कर लीजिए सर तो फिर इसके तो कॉम्प्लेक्स प्लेन में जो एरिया होता है और जो रियल प्लेन में होता है वो डिफरेंट चीज है हमारे पास
नहीं मेरा ख्याल है कि आई थिंक यू आर दिस
अच्छा ये मैं मिटा देता हूँ.
तो f of z को ये लिखो
x y v.
इस dz को
dx plus x.
I dy W लिखो और इसको तो फिर चार टर्म जो करेंगे
You remember, right? Yeah, exactly. Iota, 2 terms, yes. Exactly. And you remember yesterday we have studied that we said that let's make it as a path and like a parametric equation for this path. And that parametric path you can write this as, let's p is a parameter, right? Then you can write dx as dx over dp. So it tells you that you can go on any path, there is no problem at all, from one point to the other point. So
एक डिपेंडेंट वेरिएबल है, एक ही है, आप इधर से शुरू करते
जी,
हैं और इधर पहुंचते हैं. So you have an affine
इकट्ठे हैं. ठीक है,
सर मैं इसको थोड़ा
चले. Self satisfaction is a real satisfaction. तो लेकिन ये क्लोज्ड पाथ है सारे. एक आध एग्जांपल कर लेते हैं आज, फिर देखते हैं आगे क्या करना है. ठीक है, इसको अंडरस्टैंड करने के लिए. सो लेट्स डू इट लाइक f of z is. By the way, I recommend you to attempt the problems of Arfken. Perhaps they are slightly difficult, but you can always attempt the problem of Rayleigh-Hobson, because some of them are very simple, some of them are intermediate difficulty level. So the learning these tools is to apply on the problems. There is no other way to repeat the lectures. Just apply it and see if things comes out rightly or not, right? So you have to do is f of z is, yes please. कोई नहीं, बहुत सारे हैं. जी ठीक है.
तो वो वहाँ पे फंक्शन डिफाइन नहीं है,
हम्म.
यही कह रहे हैं. इक्वल्स टू z नॉट को अगर हम ले लें तो वो z नॉट पे डिफाइन नहीं है, वो इन सब का काउंटर वो पॉइंट है. ठीक है, अब इस केस में वहाँ पर वो फंक्शन डिफाइन नहीं है उस पॉइंट के ऊपर. अगर आप वो जो काउंटर है उसके अंदर इतने सारे पोल्स है कि वो उस मतलब उसके अंदर कहीं पर भी फंक्शन डिफाइन नहीं है, तो फिर हम उसको किस तरह से सोचेंगे?
वो यही तो बात चल रही थी कि
वो कर्व किसी पोल
जी जी
वो या तो इस तरफ होगा या उस तरफ. सिर्फ जब
इन साइड का कर्व जो है वो हमारे पास बहुत सारे
कर्व से मुराद क्या है? एवरीथिंग इज अ कर्व. क्लोज कर्व, ओपन कर्व. क्लोज कर्व की तो बात और
वो जी
ओपन
तो जी जी.
दो अलग अलग चीज.
तो कॉन्टूर है.
एग्जैक्टली उसी की मैं बात कर रही हूँ कि वो इनक्लोज फिर नहीं होगा. हमने उसको कह सकते कि अगर इनफाइनाइट पोल्स आपके पास उस काउंटर के अंदर आ जाते तो उसको फिर हम काउंटर नहीं बोलेंगे.
आप कॉन्टूर
बना ही नहीं सकते ना जगह.
वो डिफाइन नहीं है उसको.
अच्छा, आप क्या जोड़ सकते हैं दो पॉइंट को जो 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 जोड़ने से इन्फिनिट हो जाए? जो दो पॉइंट्स को जोड़ना है आपने, जहां पर इन्फिनिटी आ रही थी उसने उसी को खत्म किया ना आपने. जोड़ सकते थे, वहां तो एक सिंगुलैरिटी थी ना, आपके पास एक पोल था. क्या जोड़ सकेंगे आप उनको? फिर क्लोज कंटूर बना ही नहीं सकेंगे ना. जी ठीक है. The whole idea is this one. You calculate it in a small circle around that singularity. The answer in a bigger contour which is closed, and closing all these small circle is sum of the residues of all these terms. This is the residue theorem, right? Okay, no problem. Maybe it's better to draw it once for you like this one. If you cannot join the two, it means that you cannot make a closed path. Exactly. अब ये लाइट पोल की तरह का पोल आपको लग रहा है. How about this integral? F of z over f of z is equal to, let's say, cosine az over z squared plus 1, because this is just cosine az over z plus iota into z minus iota. I just want to ask you to calculate the contour around z is equal to iota. For z is equal to iota, not minus iota. You can do for z is equal to minus iota, but no problem. What will be the answer? Quickly. So you can see that for z is equal, around this point you have to calculate, right? So z minus 1, z minus iota is a simple pole. If it is a simple pole, its coefficient is the residue. So what you can do is, you just have to collect the residue. What will be the answer then? Okay, so the residue for z is equal to iota is limit z goes to iota, and then you can multiply this with z minus iota to this one, cosine az over z minus iota into z plus iota, and then this is gone, and you have, then you put z is equal to iota, so you have cosine a iota over 2 iota, which is cosine hyperbolic a over 2 iota. Perfectly fine, no problem. This is your residue around z is equal to iota. So if you have so many terms, you can calculate all these residues, add them, then you can calculate the integral on any closed path. I will prove one more general theorem, and I'm not sure if we have. Let me state it today, and then we will see that if we can prove it in next 5 to 10 minutes. But I'll try my best to prove it because we know all the ingredients, So now we have to prove things in a general way. So let me erase it and then do it for you. Actually, I'm defining 3 steps to calculate the integrals. The first thing is, if the pole is not simple pole, for simple pole there is no problem. If the pole is not simple, then you can still calculate the integral. Just follow these 3 steps. So calculate, the first step is calculate, let's say z minus z naught. The pole is at z naught. And then you can write f of z, to the power k. And k is greater than equal to some n positive number. You can write, multiply your function with z minus z to the power k. One thing. Second thing is differentiate it. And this is first. Second is find the k minus 1th derivative with respect to z.
I think you want to say calculate in the limit that
Z tends to z naught. Exactly.
So you have to say.
Okay. Limit z tends to z naught. Okay, d by d z to the, everything you have to calculate in the limit z goes to z naught, of course. Then you have to calculate the derivatives, d z to the k minus 1 of z minus z naught to the power k f of z. K minus 1, yes, of course. And then the third step is, then you have to do is, you can calculate the residue. I can define this residue as like this, which is equal to C1, and that is 1 over k minus 1 factorial d k minus 1 over dz to the power k minus 1 of z minus z naught to the power k f of z. So idea is the following: calculate z, multiply your function with z minus z naught to the power k, take a derivative 1 power less than that k, and then the residue will be the derivative that you have calculated for at z is equal to z naught, and you have multiplied it with k minus 1 factorial. By the way, if you look at for simple pole, this is very fine. Z naught, you can take a derivative, and this for simple pole there is no problem. But this is for the pole of higher orders. Can you prove these statements in general? Any suggestion to prove them? And always remember, my f of z is this one. Let me do it. F of z is summation n is equal to 0 to infinite a n z minus z naught to the power n plus summation m is equal to 1 to infinite. It's fine? Okay. What you have to do then? First, you have to multiply z minus z naught to the power k to f of z first. Let's do it. Then I'll put z minus z is equal to z naught. So you can write it as summation n is equal to 0 to infinite a n z minus z naught to the power k plus n plus summation m is equal to 1 to infinity Cm z minus z naught to the power k minus m. It's fine? Then what you have to do is you have to take derivative with respect to k minus 1, and k is greater than n, you remember? And then you have to take dk minus 1 over dz k minus 1 of this whole stuff. What will be the answer? So you have summation n is equal to 0 to infinite an, you have n plus k minus 1 up to so on, right? And then where you stop? N plus 2 and then z minus z naught to the power n plus 1. You can just go home and calculate it. Okay. k minus 1 है ना, तो एक ऊपर रहेगा ना उससे. And then plus C1 k minus 1 factorial. Can you justify this thing? Exactly. Once you differentiate, soon you have anything less than k minus 1, the integral will become 0 because that will become a constant then. Try it, and if you are not able to do it, I'll do it next lecture. And then what you have to do is you have to divide it with k minus 1 factorial, take z is equal to z naught, and you can see that all these terms are gone, and what you have is C1. So the third step, if you implement this step, then you have C1 k minus 1 factorial is equal to d k minus 1 over dz to the power k minus 1 z minus z naught to the power k, and f of z at z is equal to z naught. And if you divide with k minus 1 factorial, then you have the residue. So this is the most general way to prove for any kind of a pole that you have. What you have to do is first multiply with that, with z minus z to the power k with the pole term, take the differential, and then find the residue. I'll implement it to some example in next week's lecture. So we'll start from this point. So if you have any questions, you can ask. मैं फिर वो डिस्कशन में आज नहीं हो सकूंगा, लेकिन इफ़ यू हैव एनी क्वेश्चन, इसलिए मैंने थोड़ा सा जल्दी छोड़ दिया. सो यू कैन आस्क एनी डाउट, एनी सजेशन, इम्प्रूवमेंट, क्लैरिफिकेशन जो.
Just comment. I think if you had done integral dz over z to the n, then it becomes very clear what it's all about.
इनको दे दूं करने के लिए नेक्स्ट वीक में.
Integral
dz
z over z to the n. A little circle.
exactly.
All residues
immediately exactly. दोनों तरीकों से कर ले. तो ये असाइनमेंट है नेक्स्ट वीक के लिए.
आंसर आप लोगों को पता है.
चले जी जी. यर्गन कहा करता था ना, जो जर्मन प्रोफेसर आया था पाकिस्तान, तो कहता था ट्रस्ट इज गुड बट कंट्रोल इज बेटर. तो ट्रस्ट आपको है कि आंसर क्या है, एक दफ़ा कर लें, कंट्रोल भी आ जाएगा. ओके, सो इफ नो मोर क्वेश्चन, देन थैंक यू वेरी मच.